because they couldn't work. So they work only 4 hours. Then the wind starts and the whole day they can't work anymore. They skip tomorrow.
Oh, okay.
Yes.
I see that one is not working.
Yeah, no, it won't. Usually it will also come on.
Oh, I see.
Yeah, it's just the wind direction.
Okay.
Yeah, it
Oh,
will
yeah.
come on and it will fall.
Okay. So it's so that it can take wind from all directions.
All directions.
So this one is that way and the other one is here.
Yeah, and basically the process we're going to be using here at Daures to basically produce our ammonia or green ammonia is called the Haber-Bosch process. So the Haber-Bosch process, like I said, has been around since 1909, which was first developed by Fritz Haber, and then basically industrialized by Kaire Bosch. Maybe all use Bosch appliances in your houses. So yeah, so basically I just wanted to clarify that because I know there's no time, but yeah, so this green ammonia plant, we aim to produce about 100 tons of ammonia per annum and about 18 tons of green hydrogen. And just to mention that green hydrogen here, we're using it's an ingredient or component to basically produce our ammonia. Yeah, so basically what you see around you guys here, these are all the apparatus that we're going to be using to basically produce the ammonia. So maybe because of time, I'll just explain this as I go what each machine does. So yes, so basically on your right hand side, that's our hydrogen production unit, or green hydrogen production unit, where basically we are going to have the pumping in the deionized or mineralized water, as well as adding 30% of KOH. Basically, okay. So here is where we produce our hydrogen. We produce our hydrogen, and then basically we have two electrolyzers on our site currently. But the electrolyzer we're using here is basically called an alkaline electrolyzer. This is the oldest type of electrolyzer you can find. We are using this electrolyzer because it has a lot of research, and basically that was it has a lot of research as well as cost, and also like it's advised for industrial stage right now because of that research. So like I said earlier, we are going to be bringing demineralized water or deionized water, which we are going to be putting in with this pump of ours, this blue pump, which is going to be coming into our buffer tank. So in order for electrolysis to happen, an electrolyte has to be applied. So that electrolyte we are going to be using is basically called potassium hydroxide, which we basically now have to add 30% of that, so it can facilitate the unbonding of oxygen and hydrogen. So basically those hydrogen and oxygen are basically collected at the cathode and anode, which are those two bars here. Yeah, so which are basically now embedded inside the electrolyzer. Like I like to basically give an example of like in high school, if you remember, you used to have like a beacon and then a baker, and then they put like salt, and then they put like 2 wires and they put a wire, and bubbles form. So basically that's hydrogen being produced. It's just that here like it's made in a larger scale and made in a larger scale, and also more a bit more pure. Although alkaline electrolyzers produce about 99.8 purity of hydrogen, which that's why this other section is all about cleaning the hydrogen to make it as pure as possible and dry as possible. So yeah, so basically when the hydrogen is produced, or like you guys like saying green hydrogen is produced, it's basically now collected in these two pipes, which basically come along to these two buffer tanks. One buffer tank is for hydrogen, so this is for hydrogen, and this is for oxygen. Currently, we have no use for oxygen currently, so all we are doing is venting it out. So but then hydrogen, since it's not fit for SOE standards, which is grade 5, we still have to further treat it so that it can reach up to 99.999 of purity. For it to basically now be safe for our catalyst, which is going to be inside our reactor there. So most of the other apparatus that you see here are just apparatus to dry. We dry hydrogen, we deionize it. It's like I said, it's not yet clean, so you have to deionize it and dry it as well. So as long as it passes the dew point of negative 60 degrees Celsius, then like it will be safe to basically transport to our compressor. So basically that's where we aim to produce our green hydrogen. And then basically on your right hand side, or sorry, on your left hand side, that's now where we are going to be producing our hydrogen through a process called air separation. We basically just take the normal air from the surrounding and then basically convert it into nitrogen. And then basically we then go along to our first compressor, which is the one on my left-hand side, which is normally called the raw material compressor or feeding compressor. So the Haber Bosch process requires actually four things. One is that you have hydrogen, the other one is that you have nitrogen, and the other one is that you have high pressure, and the last one is in terms of temperature. So basically, and also like the ratio in terms of chemistry is it has to be a ratio of 3:1. So basically, we're going to pump our hydrogen and nitrogen in a ratio of 3:1, which is going to go into our first compressor, which is our feeding compressors. So we are going to compress that to about 100 bar, and then basically pass it along now to our ammonium synthesis kit, which goes into the buffer tank and then goes to our reaction chamber where we basically react it or facilitate it with a catalyst. The catalyst we are using here is iron flamings. So basically, when you just use one compressor, the efficiency that time it will be around like 60% to 70%. So to increase that efficiency, we basically now we'll install another compressor which basically recycles whatever might not reacted at the initial state, so that it basically comes back, so pumping up our efficiency to about 90% of ammonia production. So yes, and then basically, in order for us now to basically have the ammonia in liquid form, we have two condensers here. One condenser is what is responsible for it. So basically, we are going to use the process of liquefaction. We are going to liquefy the gas. The ammonia is in gas form. We're going to liquefy it out to -13, so you can convert it to liquid form, and simultaneously storing it in our buffer tank, which is a volume capacity of 5.1 cubic meters. So that's the whole process of how we are trying to basically produce the green ammonia. And in the future stage, we now have to produce our green fertilizer or liquid fertilizer. We're basically just going to extend our pipes to our ammonia tank and basically go to a new facility, and then basically now creating ammonium sulfide. Yeah, in terms of wiring, in terms of all the components. The only thing that's currently offsite right now is our pipes. And hopefully come early October, we'll basically be ready to switch.
So, with hydrogen, one thing is that test needs to be conducted. So the pipes actually went in for a period of almost a month and a half, just to do pressure tests. And it's different type of pipes, and every specific pipe and fitting needs to be tested and certified and signed off. So as you can see, once you get in our electrolyzer room, so basically if we say now, we put in power, because there's already power, and we power that house, now we can actually produce green hydrogen. So the green hydrogen unit is a plug to play. So once you see it's complete, it's ready to run. But then for us now to transport that green hydrogen, to convert it to ammonia, which is what we are doing here, so we need the pipes to do that. So this unit on its own, it's factory accepted and tested, everything it can produce green hydrogen. But then it's just that ammonia part that we need to connect. But then because of the safety of its nature and the training, as you explained, part of my welcoming remarks is that it's the first being done to do the ammonia here. So most of the timing, the installation, we always rate it as a 95% done, because it's just plugging on the pipes, because everything was already tested, everything has been here. But then the training part is what is going to take time. So that's why for us to be safe, we can produce end of August, but then again, we want to train, and that's part of the agreement that we have with our OEM manufacturer, so that at the end of the day, this plant, as you can see, it's going to be operated by 100% Namibians, and that's why we give it time.
Greetings, my name is Ambilaleni Poles. I'm a part of the A2D Knowledge Dissemination Program. It's a 10-day training program, and I'm excited to learn about the green hydrogen. I would like to know more about how to go about green energy and clean energy sources, and also just to learn about the ammonia that they're talking about, how to produce the ammonia sulfate fertilizers, and yeah, basically green energy.
It's such an eye-opener. We've seen presentations, we've seen PowerPoints, but to first-hand experience it and to really understand all the mechanics of this village, I would definitely call it an inclusive ecosystem. We went to where the hydrogen will actually be manufactured, understanding the electrolyzers, having a look at all the very technical machinery. From there, also went to the water treatment plant, was able to better understand how the water is being treated. As you can see, I'm a scientist today, so I've got, we were able to do a test to better understand the pH levels of water as well as the nutrients. And then we went to the agri side of the village, where cucumbers, red peppers, green peppers, yellow peppers, very delicious cherry tomatoes are all produced, and they already have off-takers, specifically the Rongo region. And I think with that coming to the laboratory, which is definitely a state-of-the-art lab, it shows that Namibia is not only playing catch-up, but we're operating at international standards. So we're very excited about the prospects of this hydrogen village, all the byproducts, some conversations around some new opportunities as well. And really it's just been a very positive experience. I'm excited for more Namibians to come and experience and see the green hydrogen village.